The next presentation dealing with the topic flat charge, discharge, high voltage hydrogen battery simplifies electric appliance from NILAR Batteries, and the presenter is Professor Dag Noreus. Give him a big hand, please.
Thank you. I hope you can hear me. It's a small group here, so maybe we can have some interacting presentation here. So welcome with the questions during the time. I can give some background maybe. I come from Stockholm University, and I spent my postdoc here in Daimler-Benz a long time ago, 83, when they were working with metal hydrides in cars and also in batteries. Daimler-Benz had a big activity in the metal hydride battery, and then hydrogen storage and metal hydride. And from that we have been carrying on to do to batteries. And I want to compare a little bit. We talk a lot of lithium battery, but there are some similarities of batteries. We can say hydrogen battery. If you have hydrogen as the active species, then you have lithium battery. Sodium battery, manganese battery. And I want to look at the similarities and differences here, although they are more similarities than differences in a way. First we can look at the some philosophical way to look at the lithium and hydrogen. So lithium is usually metallic, 0 valence state and +1 it can be. Hydrogen on the other hand is a very polarizable atom. Polarizable meaning easy to distort the electron cloud. And it's in a way to store electrons. I mean, the chemically energy you get out of the battery is when those loose electrons on the hydrogen, it sort of fits into the octet on oxygen. This is more or less common of all batteries. And so the hydrogen is flexible. It adjusts to the surrounding atoms, smoothes out electron density. It's very forgivable as an atom. And if you look in solid states chemistry, there is no other ligand that can stabilize so many different formal oxidation states. You have this old rhenium 7, formal oxidation state 7, a D0 state, all the way to cobalt, D10. It's 8 oxidation step. No other ligand can do that. So in a way, hydrogen is very unique. And I want to emphasize the uniqueness here when you do it in batteries. That simplifies a lot of things. If we look at the anodes first. In anodes of a metal hydride battery, you have sort of metal alloy, and hydrogen is stored in between. In a lithium battery, you have carbon, and lithium is stored in between. Average density is about the same here. You can use gaseous hydrogen in this. Then you have this satellite hydrogen batteries that are used in satellites. Longest lifetime of all batteries. Hydrogen battery, we have gaseous hydrogen. So anodes are similar and charged about the same capacity. The difference is more in the cathode. Although they are usually based on similar transition metal oxides. Most batteries use cobalt oxide, and you get a higher voltage of that. And it's essentially the lithium-oxygen bond that gives you the high voltage. In a hydrogen battery, you usually use a nickel oxide, but you can also use other oxides. And essentially the oxygen-hydrogen bond that sort of stores the chemical energy. So the difference is voltage, and this is of course gives a lot beneficial for the capacity of a lithium battery. But it also gives a lot of problem, because the high voltage creates a lot of side reactions that are difficult to control. We can see that also in the cathode reactions. We only get, when we discharge the battery, we can only get half an electron volt here. because you cannot sort of remove all the lithium from the cobalt oxide, because then it will decompose and release oxygen. So the difference is not the sort of scaled 4 to 1.3 here, because the capacity of the cathode is more effective in the metal hydride battery. And one big advantage with a hydrogen battery is that you can use a water-based electrolyte. This is 2 orders of magnitude higher conductivity. And this also makes it easier to make thicker electrode, more robust battery. In a lithium battery you need very thin electrodes and very thin separators and very high quality, and this drives cost up. So in the end there's not so big difference between the storage capacity of the different batteries. Best is of course the cobalt containing, then you have the phosphate and the manganese, but the metal hydride battery is not so far away, or what we call the hydrogen battery. And in the water-based electrolyte you can sort of chemically control overcharge and over-discharge reactions. So you have a little bit less capacity here. And when you overcharge the battery, then this will pick up hydrogen and it will sort of go into the metal hydride. And if you have not enough capacity here, it will take hydrogen from the electrolyte, releasing oxygen. And this oxygen can then be consumed on the metal hydride, on the anode. And when you over-discharge, then you're trying to push hydrogen back here, but it's not space enough. So you will have a illusion of hydrogen. But then you have an empty metal hydride in the anode, so that will take care of that. So with a hydrogen battery you can sort of build in the overcharge and over-discharge reactions in the battery. And one can point out the overall reaction here is of the battery contains no electrolyte and the solid phases. This makes it a very flat discharge. This is compared to the alkaline battery. Here you have a very flat discharge. A lithium battery is more sloping, and you cannot discharge it too much here, otherwise you kill a battery. And you cannot overcharge it. You have to chemically control. You have to electronically control that, each cell of the lithium battery. And lead acid battery is sort of the main this is discharge curve of a lead acid battery. It's rather sloping and not so high. If you try to drain it out to the higher discharge rate, the slope increases. So what you can do here with, if you have this flat discharge curve and you have control of the overcharge and over-discharge reactions, then you can combine cells into modules. And this is sort of the main benefit of the NILAR battery that is presented here. That and by having a flat surface, and you can create very uniform conditions, electrochemical conditions for the battery. Meaning you have a good control of the overcharge and over-discharge. So you can then build modules from based on these 12-volt packages. And still with discharge about 12.5 volt, then you have flat characteristics, and you get a chemical controlled overcharge reactions. So then you can make these sort of 12 cells modules to create into larger battery packs. And these battery packs, these modules then can be constructed into high voltage battery packs here. So it's a simple modular system of rather robust, battery modules with a stable chemistry, and the chemistry controlled then overcharge and over-discharge. So this is a somewhat complicated picture, but this shows the cyclic stability of these modules. So they are cycled at 0.5 charge discharge rates. It's sort of 2 hours charge and 2 hours discharge. And what you see here is the voltage. So this is the charging voltage, goes up to 1.5 volt, and the discharge falls down to 11.5 volts here. And then we do some capacity measurements in between. So this cycle is very stable. And also the discharge voltage you see here in the end voltage is very stable. This is temperature of the module. And this is the internal pressure, the gas pressure of these recombination reactions. With time, the maximum pressure actually goes down here, so the battery model improves with time. So the possibility to do this chemical alignment of the cell, that produces a very stable module. And you can, there was some discussion before about metal hydrides with high self-discharge. But this is mainly sold now with better separators. So this is the self-discharge rate versus theoretical capacity. You have one little quicker interaction in the beginning, and then you have a rather linear decline here. And if you look at longer times, then we had not so much data, but we had data from our stored modules. And it looks like this. We usually store the module about 75% state of charge. And then when we deliver them, you can measure the storage capacity that left. So this is sort of this 100% of the stored capacity. And this is days. So usually after a year or so, you still have a high capacity, half of the capacity of the module. So it's in a way ready to use when you take it out of the store after a year or more. And this is all done because we have better control now of the surface. The surface is a trick of the metal hydride. This is made small letters, but the surface reaction should protect the hydride from corrosion, be electric conductive, and it should transport hydrogen between the surface to the interior of the metal hydride particle. And it also be catalytic in breaking and forming this OH bond. The chemistry is mostly in the OH bond here. Similar like in the lithium battery, it is this oxygen-lithium bond that is transmitted. You have all these transition metal atoms just to have a suitable oxygen in a way for this. And this is fairly well-controlled process. And I got a question here from the company, how long can we store the modules? So we had an earlier effort here about 20 years ago when we made similar batteries, D-size cells batteries. That has sort of been in my desktop for 16 years. So I took those batteries that's from that pack on my desktop, and so the reconditioning it. You need to recondition if it's stored very long. So these batteries have been stored for 16 years, sort of discharged. And then you need, and this is sort of the capacity, and the nominal capacity is 6.6 amp hours. And after sort of 1, 2, 3 reconditioning, you're back to the full capacity. I don't think there's any other battery that can do that. Lead acid usually killed after 1 year. Sony is very proud of their battery. They say they have 60% left of the capacity of the old battery they made 20 years ago. But metal hydride battery, you have 100% of the capacity of the batteries. So I think this is a very stable solution due to the simple chemistry. This is a water-based chemistry. So calendar life exceeding several decades you can expect from this. So the conclusion is that if you cycle a lithium battery like a hydrogen battery with overcharge and over-discharge, it will not survive very long. But if you cycle a hydrogen battery as carefully as you have to cycle a lithium battery, it will survive almost forever. Because in a lithium battery you cycle within in the voltage range. You never sort of go into the deep discharge or even close to deep discharge, or you never sort of overcharge it. This you can do with the hydrogen battery. And in the end, maybe I can have some argument that batteries are not actually so rechargeable as they like to say. You can make a battery an electrochemical, but almost any redox couple. And we usually understand the main reactions of these batteries. And the main reaction, if you look in the handbook, it should say zero current, infinitesimal small currents, then it's valid. But in a practical battery, you want to draw current and you want to charge the battery. And these sort of non-infinitesimal currents, they create gradients, temperature gradients, electrolyte concentration gradients, and they fall over complicated surfaces in the battery. And they drive a lot of parasitic reactions, still unknown, entangled. And when you discharge a battery, all of these must be reversed exactly. So a battery, recharge a battery is actually an unstable system when you use it in practical life. So it's more like weather. Recharge a battery or chaotic system. And the higher the voltage you have, the more problem you get. Because the higher voltage will drive the parasitic reactions, making it worse. Here. And we can see that the throughput, this is a somewhat complicated picture. So here we have, we cycle batteries at the state of charge swing. If you cycle them 100%, then you can cycle them, go down to 20% cycle state of charge. And this is from Varta. And they compare lead acid battery, flooded, AGM, lithium batteries, and metal hydride batteries. So if you cycle it 100%, you get about 2,000 cycles here. If you reduce the cycling to 50%, of course you lose half the capacity in a way, but the numbers of cycles goes up. So the throughput of your battery will increase. And the throughput of the battery over lifetime is more important. So this, as you have a more shallow cycling, the battery will survive longer. So this also sort of the battery electrode material helps to remember its state. So this reduces the negative influence from the parasitic side. That helps. But you can also reduce it by increasing the quality. But that increases cost. So either you don't charge or discharge your battery, or you make a very high quality battery. And the higher voltage you have on the battery, the more difficult it is to make a high quality battery. So to sum up here now, a hydrogen battery has a low cell voltage, so bad for capacity, but make parasitic reaction easy to control. And it's very beneficial for the choice of electrolyte. You can have a water-based electrolyte, and separators, no major problem. And this is got to, thanks to the highly conductive water, you relax quality control of the production, meaning you can drive down costs here. And very importantly, the water-based electrolyte makes it possible to control overcharge and over-discharge chemically. So you don't need to have external control circuits to do that. And what's the latest now with the NILAR design is that you, if you remember, you don't need any substrate, because the current is drawn sort of through the battery pack of this module. Well, we can go back to see that. So the current goes through this direction, not out to the end of the plates. So you don't need the substrate to it. So we are sort of on the hydrogen exhibition here. And so the hydrogen batteries are kind of precursor to the hydrogen economy. And it resulted a lot of metal hydride research, initiated by the oil crisis in the 70s. And at the moment, the favorite choice for hybrid electric vehicle. Most of the Toyota cars use this hydrogen battery. And you have a simple water-based chemistry, can reach high performance. You can make robust battery, and easy to disassemble those electrodes that have no conducting electron lead here. So easy to recycle. You just separate powders from each other here. And with this makes it possible then to make larger battery packs from modules. And there is a stand C50, I think, when they are more willing to discuss in detail here chemistry and how these are built. So a few minutes left for the discussion or questions. So please.
Thank you very much.